So, what I'd like to do today is chat with you about the full cycle of a deep learning project. And as I promised in the first lecture, rather than me talking at you for an hour and 20 minutes or whatever, we'd love for this to be much more interactive. And so what I'm going to do is illustrate this with an example, but also ask you a bunch of questions along the way about what you would do if you are the one working on the project that I'm going to use as an illustrative example. Okay, so plan for this to be quite interactive, and please interrupt anytime and ask questions, since I think that's why I want to do this in person here at Stanford. So one of the reasons why developing machine learning or deep learning or other types of AI projects, including AI projects using large language models or agentic AI workflows or whatever, is that AI projects are different than traditional software engineering projects. So one of the biggest differences between AI projects of the many different flavors, supervised learning, LM-based, generative AI-based, is that in traditional software projects, you write code and you control your code, right? Write whatever code you want, compile it, your code does what you tell it to. But AI projects, involve both code as well as data that you train your algorithm on. And you almost never know what strange and wonderful things there are in your data. For example, if you're working on a face recognition application, that's a running example I'm going to use today, then as you're just getting started on the project, it's really difficult to know in advance what you find in the data. Is the lighting of the faces good? Do you struggle with people with very long hair or people with short hair? Do people making weird facial expressions make your system struggle? Do people wearing glasses make your system struggle? So data is so rich that a lot of the time you can't predict in advance what your AI system is going to do, not because you don't control the code. You can write whatever neural network or whatever code you want, but you don't know what's in the data. And this is why, unlike traditional software engineering, machine learning development is a much more iterative process where you just have to build something, see how it works, and then through a process, almost discover what is in the data and therefore what you should be doing to change your code to make your overall system perform. And this is also true, not just for deep learning based systems. This is also true for modern large language models. There's been a lot of hype buzz about how LLMs, large language models, are hard to control. I think there's a lot of excessive hype about that, kind of fear mongering. There's a little bit of that. But one of the reasons why none of us know in advance what LLMs do is because it was trained on a lot of data, more data than any human could possibly look at. And we just don't know, with precision, what is in all that data that the algorithm was trained on. And so because we don't know the data, we can't really look at all the massive tens of trillions of tokens of data it was trained on. It's hard to know exactly how a large language model will perform, which is why building agentic AI applications or building large language models-based applications is also very empirical or very experimental, meaning you just have to build something, then see where it goes well, see where it goes poorly, and then use that to fix problems, and that's how you drive progress. That makes sense? So because you control your code, but you don't really know, it's hard to control the data. And this is true both for the data you have stored in your hard disk. Kind of, terabytes of data stored in my hard disk. I don't really know what's in my hard disk. And the thing you really don't control is what data the world will give you in the future. So we deploy a system in the world, say face recognition, which we should talk about. Will people wear a thick, heavy scarf that covers part of their face when it's winter? You just don't know. There are all these things in data that will surprise you. And if you don't even control your past data that's already in your hard disk, you certainly can't control your future data. So it turns out that a lot of machine learning classes talk about building models, right? And you learn a lot from the online videos about how to build powerful deep learning models. But it turns out that building an overall machine learning system or a deep learning system has a lot more work than just training models. But if you look at a lot of courses, there's actually a very strong focus on modeling, because I think that's what academia has focused on, right? We can train models, evaluate models, publish papers on models. And so you find that a lot of courses focus on, training a good deep learning model. And that is absolutely important. But because we know how to evaluate models, different research groups can benchmark different models. There's a lot of academic research work on that. That's reflected in a lot of courses. But this is just a small part of what you need to do if you want to build an effective deep learning system. And what I want to do today is go outside the small box of models to give you a broader view of what it feels like to develop a deep learning or AI or machine learning system. Okay? And this is what it often, this is what building a deep learning system would be like, which is first, right? Specify the problem, figure out what we're actually working on. The running example I want to use today will be to build a face recognition system or face rec system for security, for deciding when to unlock a door. And I know Kian talked about some face recognition, which I believe face rec architectures last week as well. But specific application I want to talk about is something I've worked on. I built one of the commercial systems that for this is if this is a door, and this is you or a friend or maybe someone that you don't want to let in approaching. If you have a little camera, sorry, bad drawing, take a picture of whoever's approaching the door and decide whether or not to unlock the door, right? So face recognition to decide who's authorized to enter, like a restricted location, like a corporate office building or your house or whatever. And actually one common use case that one of my teams built was swipe keycards. So sometimes keycards get stolen. And so one of the systems we deployed, fairly large office complexes was if you swipe a keycard, we also just take a picture, then soon discard it to make sure that the key card is held by the person, whose face is shown on the key card. So it makes it harder if someone to steal a key card to gain unauthorized access to like an office complex, right? So I'm going to use this as the motivating example for today. And after specifying a problem, typical process is then, right? Sometimes the open source models you can download, but let's say for today that the open source models aren't good enough. You want to train your own model. But the typical process will be get data, design a model, train a model, and then we will iterate through these steps a bunch of times until the model looks like it's performing well enough. And then after that, we have to deploy it. And monitor and maintain the model. Okay, so I'm actually going to talk a bunch about multiple of these steps today because I want you to come away with a feel for when you're working on a real machine learning application, what the important steps you will face are, right? And so as I alluded, machine learning development is a very iterative process. So for these 3 steps, we often drive a rapid development loop where we design the model, train it, analyze the results, and then maybe design or update the model or the data or something, and iterate around this loop many times before you are satisfied. And all right, just one more detail. It turns out that for face recognition, the very common architecture, which you learn in detail about later in the online videos, is a neural network called a Siamese network. And what that does is a neural network that takes as input 2 pictures, and two pictures get fed to a neural network or a deep learning algorithm. And it's a job of the deep learning algorithm to tell us, are these two pictures the same person or different persons, right? Because if you're trying to set this system, say for your house, and maybe you have, I don't know, a few family members or roommates you want to let in, then it'd be quite annoying if you had to retrain a neural network for every single home. So the most common way to do face recognition is to have a neural network that inputs two pictures, and the job of the neural network is to tell me, are these two pictures of the same person? And then the way you set up the system is to input a few registration pictures. So take a picture of yourself, take a picture of your roommate, take a picture of, any family members you want to have access. So then when someone comes, it can quickly check if the person that just showed up is one of the people that's authorized, and then let them in. And in the corporate key card swipe example, if someone swipes a card and, my card says, this is Andrew's card, then I'll quickly pull up my registration picture to double check if I seem to be the same person as the, Andrew that was registered, right? So this is how, this is a typical neural network architecture. All right. So I have a question for you. One thing I'd like to do today is, walk you through a number of scenarios and invite you to think about what decision you would make if you're the CTO of a startup building these technologies, right? So my question for you is, if you're the CTO of a startup building the next face recognition system, and if your lawyers have said you aren't allowed to download data from the internet, right? So let's not download data from the internet for this application. How would you go about getting data to train the system? So what you need is a bunch of pictures of people, right? To train a neural network to say, are they the same person or not? So maybe take a few minutes to think about it, and then I'll see if people raise hands and give some answers. And one specific question I have as well is, how long would you take to collect data before you start training a model? Right. So I think, you need to get data. We've designed the model, I guess, and then you need to train model. So what does the timeline look for you? We've specified the problem, we've designed the model. How many hours or days or weeks would you spend to get data, and how before you start running, gradient descent? Right. Maybe, I see your hand up. Oh, sure. Go ahead.
Are we doing everyone around the world, or are we specifically looking at Bay Area or America? Just narrowing down the scope, or it's this wide range of everyone?
Let me leave it a bit more open-ended. Say you just graduated from Stanford and you're CTO of a 3-person startup, building this thing, that eventually, hopefully you sell all around the world, but your goal is to just get started with the 3 of you working out of, Palo Alto, California. Right? And do it as your real self, right? With the resources that you have. All right. Anyone want to venture an answer? So how would you get data to train the neural network? Go for it.
I like using some video streaming service and the video data, or maybe or asking some company to I can get the data from them, or we can even create a small video streaming service and can collect the data of people, so they can agree to share their videos.
Yeah, cool. Video streaming service. By video streaming service, you're thinking like, Netflix and Hulu, or are you thinking like security videos? Oh, like Zoom. Oh, I see. Cool.
Like video, people uploading video.
I see. Cool. Right, cool. All right, video streaming service. How long do you think it'll take to do that?
A couple of months. The reason actually machines that I will be able to collect data from the examples and people like that. People create visual expressions very quickly.
Yeah, cool. All right, cool. Thank you. All right, creative idea. Any other ideas? How would you go about and get data? Yeah, go ahead.
Because when I worked for a 3-person startup that had a larger company, I would put a camera in the plan to have the camera ultimately have the swipe and just ask the employees if they would like to participate in data collection, and you just take the pictures of the employees that we have data, so the employees that are actually working. might not be generalizable, but could get quickly college performance. Just how it is.
Yeah, cool. Awesome. Right. Stick a camera there. Let people, opt in, right, to get the picture taken. Cool. I think I saw a hand up. Go for it. Oh, sorry.
Take to direct users of all these services, capital,
I see. Cool. How would you get users?
and what the idea would be
I see. Cool. Right. Yeah. By your own people, you mean like grab some friends and also they'll give you that LinkedIn photo, give you some pictures from your camera roll. Yeah. Cool. I like that. That's fast. I like that. Any other ideas? Oh, go ahead.
Stanford begins survey of students information use their student ID photos.
I see. Interesting. Yeah. Ask Stanford to send an email. Cool. But I love Stanford. Stanford's a wonderful institution. Also, that's going to take a while. Really creative idea. I like the creative ideas. So let me share with you one guiding principle for how I would encourage you to approach this problem of data collection. I appreciate all the creative ideas, actually. One of the frameworks I often use to decide how I collect data is speed. Because I find that, actually, especially if you're building a startup, right? In my opinion, one of the strongest predictors for whether a startup will succeed and also whether a small innovative project in a large corporation, it can be a giant corporation, but if a team of 3, work on a small innovative project in a big company, I find that one of the biggest predictors for the chance of success is just the speed of execution, the sheer speed of getting stuff done. And so when I'm sitting with a team and brainstorming different tactics, I will gravitate toward the tactics that let me get a data set very quickly. And quickly usually means, like 1 or 2 days. Even if it ends up with a inferior, smaller, lower quality data sets or whatever. Because I don't really know what problems I'll see in my data. And the quicker I can, get a data set, train a model, see where it goes wrong, the quicker I can then discover what's wrong with my data and fix it. True story, chatting with a CEO that told me he actually had spent, I think it was over $100 million, definitely more than tens of $millions of dollars, spent a lot of money buying a company for his data. And then he actually said, "Hey, Andrew, I spent all this money to get all this data. Can you help me figure out how to monetize this, how to make money off of this?" Right. And I kind of look at him and go, boy, I kind of wish I hadn't done that. Right. And what I find is that, the value of data, it's just so difficult to know in advance, right? What's important and what's not important about data. So for a lot of these tactics, for example, I think student ID is an interesting one. But, are student ID photos weird in some way, right? Or are they too expressionless or are people smiling too much in student IDs? I actually have no idea. Actually, my Stanford ID, I look really weird in my Stanford ID. And I think and actually like the idea of sticking a camera and just letting people, come up and opt in and take a picture if you can do it quickly. And I think in a big company or even in a small startup, if, it's important to respect user privacy or individual privacy. But if you can stick a camera in some place, that doesn't, invade people's privacy, that don't want to be any part of this, but let people opt in, take the pictures of permission. If you can do that in days, I find that to be valuable. One of the things I found for quite a few of my projects, found that, Stanford students, our community here is pretty cosmopolitan with people from all around the world. We're not fully representative of the world's, distribution of people, but we actually do have people from all around the world. A lot of Stanford people are actually very nice. So one thing I've done multiple times is when I need to collect data, we'll go to places on campus with high foot traffic. It turns out cafeterias have very high foot traffic. And we'll just ask people, "Hey, we're working on a project. Can I get a sample of your voice? Can I take a picture of you?" And kind of with, really informed consent, tell people, "Is it okay if I do this?" I've been delighted at how collaborative, right, Stanford students are. And I find that one thing I've often done is gone to my teams and said, we have 2 days to collect data. It's like, whatever, it's 11:52 a.m. now. Let's figure out what we can do by, what day is it? Tuesday. Let's figure out what we can do by Thursday, 11:52 a.m. So let's give us 48 hours and let's brainstorm. How can we collect data? And it's fine that the data isn't all there. Fine that the data is low quality, but that velocity lets us more quickly train a model, figure out what's wrong with the data, and then jigger or retweak how we collect data. Right? So I find that there's some teams that ask, how can we collect the data we need and how long, and then ask how long would that take? That usually leads to much slower execution. I instead tend to go to my teams and say, we're 2 days or 1 day or maybe a week, right? Some short time span like that, and say, what's the most creative, respectful, responsible, but creative way you can use to collect data in this short time span. And one of the ways to think about that too is training a model takes, I don't know, let's say it takes 2 days. Maybe I should take more like 1 day, right? If you can train a model in a couple of days, then I would not spend, like whatever, right? 2 months to find data to train a model, because then this becomes a huge bottleneck. Because you can train a model relatively quickly, let's take a commensurate amount of time to design a model or design the data as train a model. And depending on how long it takes to train a model, sometimes training a model, needs to run overnight. I actually see teams sometimes take 1 day iteration loops around this. The fast moving teams I work with, we often go around this loop once per day. For the smaller models. If you're training a large AI foundation model, sometimes training a model takes weeks or even months, then the process can be different. If your model run is going to be, 2 months, then yeah, maybe it makes sense to spend, a couple months to get the data really right. But for face recognition, you could train that overnight or actually in a couple hours quite easily. So it makes sense not to spend massive amounts of time before you go into train the model. Does that make sense? And because the word empirical means experimental, right? Sorry, I've used the word a few times today. And I think we say that machine learning is a very empirical process, meaning it's a very experimental process. You have to do it, see what happens, and decide what to do next. I know that sometimes others have criticized our field as like, we never know what we're doing. We just try stuff and see what works. And there's a little bit of truth to that. I think understanding neural networks, hyperparameters architecture, that is really valuable. So we don't just try stuff at random, but because we don't know what's in the data, we do try a lot of things and then drive a disciplined process, understand what works and what doesn't, and then use that to navigate forward. Does that make sense? And then I'll just say there's one exception to the advice I'm giving here, which is if you're working on a project that you have worked on many times before. So, whatever, I've built a bunch of face recognition systems. So I kind of have a sense from previous experience and from reading research papers that certain things I know are just not going to work if I have, 100 images, right? So there's some face recognition systems I know I probably need at least 50,000 images before it'll have any hope of working. So because of that prior experience, having gone through that loop a lot, I now have a basis to say, okay, I do need 50,000 images, then I might invest upfront and put more effort upfront to get those 50,000 images. But I think for most applications you work on for the first time, if you don't have a academic literature to justify certain larger data investments, or if you don't have the prior experience yourself, then I would focus on the speed of iterating around this loop. Make sense? All right. And to relate this to large language models based applications as well, a lot of you are probably, you may be building applications by prompting LLMs and calling an API, right? Like an OpenAI or Anthropic or Gemini or MetaLlama or whatever API to get things back from an LLM. One of the reasons that too is a very experimental, a very iterative empirical process is because when you write an LLM prompt, you don't really know in advance how well it's going to do because it was trained on data that none of us have really looked at. And that too is why instead of theorizing for a long time about what prompt to use in LM, just try it out. And then it's by doing that, you then see the problems, and then your focus can be on fixing the problems. Make sense? And in fact, there's a lot of discussion on responsible AI, how to make sure AI systems are safe or they don't have kind of unforeseen circumstances. And because a lot of the theorizing, you can only theorize so much. I find that if you want to build safe, responsible AI systems, one of the best ways to do that is to just build it and then experiment with it in a sandbox environment. Just don't let it out in the world until you've tested rigorously, but just go build something and then, test it, probe it in the safety of your own laptop, right? And don't let it and innocent users and have some weird impact on innocent third parties. But it's only by building it and then probing it that you can figure out where can it go wrong, where it will say inappropriate things, where will it, respond inappropriately to certain user queries. And then that tells you where the problems are that you can work on addressing. Okay? All right. Yeah. Question?
How do you use analyzing and kind of validating the results to guide that data to changing validation?
Oh, sorry, again?
So when you come up, when you do analyzing of the model, right, and you come to a conclusion that your model is not good, right? How do you use that to kind of figure out what's wrong in the data? Yeah, right.
Great question. So when you analyze something's wrong with your model, how do you use that to take the next step forward, right? That's a big topic that we'll talk at length multiple times in some of the videos and also in some future lessons. But maybe long story short, one of the things you could do is change your neural network architecture. You may realize that maybe the assignment network isn't working, or read the literature, change architecture. The other thing you can often do is change your data. So data-centric AI is the discipline of systematically entering your data to build a successful AI system. And it turns out that if you build a face recognition system, let's say, I like your hat, Stanford hat, that's cool. But let's say hypothetically that you find that the system has really struggles recognizing people that are wearing hats. Then you may say, all right, I need to get more data with people wearing hats, right? And so it's often that, looking at what goes wrong, which we call error analysis, that then gives you the insight to say, oh, it works well on these types of data or these types of users, but the struggles of these type of users in the data. So can I fix my data or get more data just on the subset of cases it struggles with? And that's a very common motion. That's a very common process for then driving the performance of the system. And this is also why blindly going out to grab more data willy-nilly, that's often not a good strategy because there's just too much data you could get. Do I want more data with people with long hair or short hair, or people with facial hair? Sorry, too much hair. Too many hair examples. Or, do I want people with, wearing a scarf covering part of the face, or people that wear glasses, or that don't wear glasses, or people that, are slightly turned away. There's just so many different types of data you could invest effort to get more of, that until you build a system, see where it goes well, see where it goes poorly, is really difficult to decide where to get more data. And just get more data of everything under the sun, that's very slow and expensive. And I think part of the hype about the value of data has led people to have sometimes overly simplistic view of data, right? Yes, of course I want more data, but just grabbing more data of all types of data is a very inefficient, very expensive way to improve my system. And even if you look at the way that frontier models are trained right now, it's not a game of just grabbing more data of anything under the sun. It is identifying the subcategories where it's valuable to invest to get high quality data, which is why if you look at, it turns out in AI, there are two clear buckets of value in LLMs, right? There's the general answering people's questions. I think, OpenAI ChatGPT is doing really well there. Gemini, Anthropic have momentum, but there's the answering general questions. And then one of the verticals is really valuable is AI for coding assistance. So I think, Claude has been ahead for a while, but OpenAI, I don't know, Gemini 2.5 Pro, some of the models are making really good progress in coding as well. And if you look at the work that the frontier teams are doing to improve coding, building iterative agentic workflows is part of it, but also finding clever ways to come up with coding related data is also a part of it. And if you want your LM to do better encoding, you don't grab data willy-nilly with low quality, random internet chat, social media, whatever data, right? But instead, having high quality coding related data is how you can have a focused effort to improve your LM's ability to code. So a lot of these things are actually, I feel like, the like more data is better. That is absolutely true, but it's also overly simplistic. Data is not monolithic. There's subcategories of data, and having a view on what piece of data to really invest in getting a lot more of. That's really important to being efficient in how you improve the system's performance. That makes sense? All right, we'll talk more about error analysis in this later. Any other questions? Cool. All right, yeah, go for it.
What about the quality of data? Like, for example, for pictures, we want to collect input plus everything is possible, good quality or
Yeah, right. So as you collect data, the quality of data matters a lot too, which is why, and I think data quality is tricky. I think when building an application for the first time, I would still focus on speed and collecting some data quickly. But as you then analyze where the system is going well and where it's doing poorly, you often find that the quality of data really matters. So, trying to decide, should I talk about this now or later? I'll come back. So let's see. Let's go there. All right. Let me talk about LM1. There's a lot of low quality random chat on the internet that's not that useful for training LMs. But I think, it's actually now well known that if you can legally access very high quality written, authored articles or books, they're highly edited, very insightful. That's very high quality data for training LMs. And I'll give an example later as well for face recognition. It turns out that, blurry images, right, would be low quality than sharp and focused images, assuming that's representative of how you want to recognize people's faces. So that really matters as well. All right. Anything else? Cool. All right. Oh yeah, go for it.
Question about the data and how close they need to be to the task we want them to do. For example, in face recognition, where you're trying to compare two pictures, we need to train a model just to compare objects, which is easier to say than people's faces. It's much faster, but we're moving away from the ideal task we want the data to do. So, what is the balance here?
Yeah, so right, just repeat for Mike. How important is it that the data you collect is similar to the distribution of things you want to work on? I think it's important, but not as important as most people might think. So it turns out that one of the reasons neural networks have been so effective is because when you build a very large neural network, you can throw all sorts of data into it, including data that is not perfectly tuned to your test set distribution, and it often doesn't hurt so long as your network is big enough. So you raise the example, what if we have it identify two identical objects, right? If it's generic objects like, I don't know, water bottles and markers, maybe that's too far afield. But if we were to use, let's say, simulated cartoonish characters, right, that look really different than real humans, my guess is it probably won't hurt at all, and it may even help a little bit. And so throwing in a lot of data, if you train a large neural network with a lot of capacity to absorb even some slightly irrelevant data, it usually doesn't hurt and might even help a little bit. But how much it helps is another empirical question that will be problem dependent, and we often just have to try it out. But I think maybe, in the past, people used to have an obsession that the data you train on has to come from exactly the same distribution as the distribution you test on. That used to be how machine learning was done, 10, 15 years ago. That's really not true today anymore. I think we're very comfortable. And I think when neural networks were much smaller, when you could train very small models, there was a sense that you didn't want to distract the neural network with irrelevant data, right? Because compute was expensive, with few parameters, and you distract it on irrelevant stuff, maybe it gets less good at the core task you really care about. But if you can train a bigger neural network, which is getting easier and easier these days, then it's become much more okay to toss in some data that hopefully isn't incorrect data. I think incorrect data would be a problem, but just irrelevant examples hurts much less because big neural networks is like a human brain, right? I don't know. The fact that I learned to play the piano, probably doesn't make me worse at AI, right? Because hopefully my brain is big enough to learn to play the piano and learn some stuff about AI. And I think as neural networks get big enough, they can learn some other irrelevant things and also do well at the core tasks you really care about. But this was less true when, if my brain was really small, then, I don't know if any are fans of Sherlock Holmes, but I think Sherlock Holmes had an attic theory that your brain has only so much capacity, so you gotta forget some stuff to learn new stuff. But when you train very large neural networks, that's much less true. Cool. All right. Thank you for all the questions. So what I want to do is just keep going through this flow, right? So we talked about your data, design model, train a model. We'll talk a lot more about error analysis later this quarter of how to figure out where your algorithm is still subpar and where to focus efforts to improve it. But what I want to do is give you a sense of deployment, right? So, all right. So when you have trained a model, it's often a bunch of software engineering work to then maybe take your model, host it in the cloud, the local server, and have it run inference, right? So a very common architecture for deploying a machine learning model will be that you have a neural network as a piece of software, you deploy it maybe on a cloud hosted service so that your software can accept a picture or accept two pictures and reply back, do I unlock the door or not? Or is this the same person or not? So there's kind of a bunch of software engineering work that needs to be done. But in practical deployment settings, I'll actually tell you, it turns out that if you're building a practical face recognition system, you probably find that if you are trying to unlock a door, to a corporate campus, it's too expensive or too slow to stream video 24/7 to cloud to classify every frame at 30 frames per second to see if, there's a person there you should unlock the door for. So in practical face recognition systems, what we end up doing, let's take the example of, someone walking up to the door, to your door at home, and you want to see if there's someone there that you should unlock the door for, right? So a lot of systems will actually have an image from the camera and then try to build a system. Right. So what we have so far, right, is a system that takes this input an image and maybe a reference image. Neural network says, do I unlock the door or not? But it turns out that if streaming video is too expensive, classifying every frame is too expensive, we'll often end up with a system like this. But VAD stands for Visual Activity Detection. And what this does is a usually low cost, low power, inexpensive compute job to run to just very quickly maybe try to figure out, is there a human face there? Because it turns out, actually, if you're building something to unlock your front door, to you and your friends, if you look out my front door in my house, it's pretty boring. There's a wall, we see over the street, but nothing moves most of the time. So there's very obviously, almost all of the time, it's very obvious that there's no one outside my front door trying to be let in, and it'd be very wasteful to stream all that video to the internet for classification, right? So visual activity detection is usually a low cost, low power system to just very quickly decide, should I do the work of sending this to the larger face recognition system neural network that may be hosted on the cloud to have it do the much more computationally expensive work to decide, 0 or 1, do I unlock the door or not? Okay. So this type of optimization in order to make the system computationally feasible to deploy is fairly common. And I'm going to give you two options for how to implement VAD. And I'm going to ask you to reflect on them and then tell me which one you would pick to get started. Okay. So option one is a non-machine learning based method, which is see if the number of pixels changed is greater than some threshold epsilon, right? So if the camera is stationary, maybe looking at a wall, most of the time the pixels barely change because it's just a wall. And so you can write a little bit of code using some image library like PIL, Python imaging library, or some simple write a few lines of code to just say, has the number of pixels whose RGB values that change more than some threshold, has more than 10% of the pixels changed compared to what it looked like a second ago, in order to see if there's anything in front of your camera to even decide to pass this to a more high part neural network. Right? Option two would be to train a small neural network right? So face recognition is a pretty complex task. You have to look at multiple cues in the face, look at the eyes, look at the mouth, look at the, so that takes a relatively large neural network. But just taking a quick glance to see, is there even a human in front of my door? That's a much simpler task. So option two would be training a very small, very low power, very lightweight neural network to just very quickly tell you, do you think there's a human there? And then use this trained model to decide, is it worth passing on to a much more powerful neural network running in the cloud with a lot more resources to make the final determination? Okay. So if you are the, again, CTO of a 3-person startup building this, how would you start? We'll give everyone a few seconds to reflect on this now. Get people's thoughts. All right, go for it.
Well, I think it's very much problem dependent. You might live in a street where people walk by every time if you want to look at some threshold of pixel change, you might get a lot of false positives. So it depends on what type of problem you have, and you can also go with an option that you can make it some simpler specification unnecessarily, or maybe like gainers, neighbors, or classification.
Yeah, right. Cool. Yeah, right. Cool. All right. Just repeating my mic. So problem dependent depends on whether you're on the street with a lot of people walking past. Maybe consider other algorithms. They're even cheaper than small neural net. Cool. Just do that.
Just a training model. Because this is not the main task. The main task is training for that. We could probably just use option one in the short term while we collect more data, and then replace that one with the second one.
Yeah, cool, great. So use option one in the short term, and then maybe replace that with option two or with more data. Yeah, cool. That's very, very sane approach. Go ahead.
I was thinking about why not using two options, because what we do, home around the pixel part is very simple. Only if Z is clear, then we kind of can say, oh, is it clear or not? And after that, moving to the one.
Oh, sorry. So use both options. Put both in the pipeline. Oh, that's interesting. I see. Oh, right. So see if let option one see if anything's changed. If something's changed, then pass to the small neural network. And then, okay. That's cool. That could work.
Right, so first we are searching for activate good, and then kind of see if it's good or not.
Yeah, cool. Yeah, that could work. So it could cascade in multiple steps. Yeah.
How much would it cost us to actually run the neural network? Because that would affect, if it's cheap to run a neural network, I don't know, limit of two options, right? Because then you don't have to worry about someone coming to the door and nothing happens. If it's more expensive, then I would
cool. Yeah, right. Yeah. So how expensive is it to run this neural network in the cloud? So, actually, so I would usually want to design both of these to run at the edge, meaning on the device.
The neural network capacity.
Oh, this one.
Yeah.
So it turns out that streaming video is fairly expensive. So I think, yeah, I feel like, boy, I don't have numbers at tip of my fingertips, but I think, running this 24/7 is not feasible. So we definitely need something to filter it down. But sending, I don't know, few images every minute is probably not a problem. Makes sense. Yeah. Go ahead. Oh, sorry? All right, sample certain frames of the video in order to get all of them. Yes, I guess so. Yes, although I think if you have a video of my front door, you need a way to sample other than random, I guess, right? Because a lot of time nothing happens unless you take 1 frame per minute, I guess, which would be okay. But then we don't want someone waiting there for a full minute before we finally get around to sampling it and then sending it. So, yeah, go ahead.
I guess this is a question. Could you use the same images that you are using to train your neural network on option 2? Or would that be biased?
Yeah, could we use the same images for training this network to train this, the option 2 network? Maybe. I think it's actually one of those things. I would say we have to try it before we know if it works. Might be doable. Depends a lot on what data we collected to train the great neural network. Yeah. Cool. Anything else? All right. Let's take a couple last ones. Go ahead.
Use option 1, keep it really low threshold. Is that anything better than paying for option 2?
Cool. Right. Yeah. How about use option 1, keep a really low threshold, so we send very few images. Is that what you mean? Yeah, I think that'd be reasonable to try. Well, right, so long as we don't miss too many people, but yeah. Right, let's take one last comment though. Share a perspective on how.
I feel like that might be a concern because if there's something like the swaying movement in that road, it's going to trigger modeling everything.
Yeah, right. Yes. So one of the weaknesses of option 1 is if there's a tree swaying in the background, or if you see a road and there's a car that drives by, or if it's a busy street, the car's driving by all the time, or if the neighbor's cat comes and visits, those will trigger this, right? So those are downsides. So let me share your perspective of how I would approach this and what we actually did. So if you're the CTO of a startup implementing this, to me, it again comes down to speed, right? And so what I would ask is, how long does it take to implement option 1? And how long does it take to implement option 2? And I think everyone made good points about the pros and cons of these two options. And if you're actually doing this, the approach I would take is, just ask, what can I do really quickly so I can then deploy it and see whether it works, and I'll fix it if it doesn't work. Because I think these insights like, will trees swaying in the background affect it? It turns out it actually does probably, but maybe not if the wind isn't that strong or if, right? But it's very difficult to know answers to questions like these because you don't really know until you stick on a bunch of cameras in front of doors and see the data. Then you can get more confident in how well option 1 works. Like, I don't know, how often does the neighbor's cat actually come by? And if there's a car that drives past, are the cars usually so far away that it doesn't matter because the number of pixels per car is small, right? So all of these are very empirical questions. It's really difficult to answer. And the fastest way to get answers is to just implement something quick and dirty and then run it, see what goes wrong and then fix it. So what happens and tell you, for what the experience of a lot of face recognition teams is, because option 1 is so quick to implement, this is like, I don't know, 5 lines of Python or something, right? And get an Alan to write it for you. Just get an Alan to write the 5 lines of Python for you. So you can implement this in, 20 minutes, maybe even less. Whereas this, I think, will take you at least many hours, maybe longer to implement. So my instinct would be to start with this. And it turns out, having built many face recognition systems, I'll tell you, this actually doesn't work well enough for all the problems people raise. And so we wind up going to this. But implementing this also gives you insights into where it's going wrong. And I'll give you one example of one insight that, we and many other face recognition teams have, which is it turns out that when you're approaching a camera that's trying to recognize your face, there are some frames that are going to be really clear and in focus, and a lot of frames are really blurry, right? If you just look at a video of someone walking toward the camera, sometimes just, when I'm stepping, sometimes the velocity of my face is higher and sometimes it's lower, right? That's just what it is. And so sometimes my face is in focus, sometimes it's more blurry. And it turns out that if you can select out the high resolution frames and feed that to face recognition, you get much higher quality results, right? So this is the kind of stuff that I assume, most people would not know about until you worked on a system like this. But it turns out that when I was working on a system like that, having a system to not just do VAD, but also capture the video and then deliberately select not just one, but maybe 5 frames that are high resolution and in focus of the person, that actually gave a significant boost to the accuracy of our face recognition system. And I mentioned this as an example of the sort of discovery that you will have only when you implement one of these systems, maybe even implement this system. But you implement this system, you see, boy, we're trying to recognize a lot of pictures from blurry faces. Maybe we could need to do something about that, right? And this is driving that empirical process that may then lead you to train a neural network, both to see if there's a face, but also to see if the picture of the face is in focus, to select out that frame for downstream processing. Does that make sense? And this is why you find that for some meaningful fraction of questions I ask in class, the thing that's the speediest to do is often the right answer, because that obsession with speed really lets you go in and figure out what's in your data and improve your system more efficiently, right? So what happens in practice is start with this, discover how it doesn't work, because it doesn't actually work, and tell you that, and then figure out, but use those learnings to do this. Yeah.
Classification accuracy is problems like this in the video.
Yeah, so is there a sense of what is a good classification accuracy in problems like these? It's actually really difficult. One of the common benchmarks, you learn more about this in the 3rd module on the online videos as well, is building machine learning systems is easier if we have a reference level of performance, like an aspirational target accuracy, which is often human level performance. It turns out that the way you diagnose bias and variance, which we'll talk about later in this course, is easier if you know what's an achievable level of accuracy. And very often we'll use what a human expert could do as the achievable level of accuracy. And then in the case of face recognition, definitely under controlled environments, we're better than humans. So definitely, actually, the AI systems we build, they're way better than I am at recognizing human faces. And I think AI systems are better than, I want to say, probably the vast majority of humans, maybe all humans at this point, at really distinguishing if 2 pictures are the same. And then it gets really difficult. Then it actually gets more difficult once you're even better than humans. But those are, yeah. But until you're as good as humans on a certain task, using a human level performance is often a good benchmark. And then if you're doing something that even humans can't do well, like it turns out, recommending online books or movies or whatever, humans are actually not that good at that. I think most of us have a hard time recommending good movies, even to our closest friends. AI actually probably does it even better than many of us do as humans. Then those things, it's harder to establish a baseline. Cool. All right. Now, one final aspect I want to touch on is after deploying a model, to monitor and to maintain the model. one thing that often happens is you train a machine learning model, works great, does well in your training set, does well in your test set, works great, and then you deploy it, and then annoyingly, the world changes and your system no longer works, right? So we sometimes call this data drift or concept drift, where the distribution of data the world gives you is different than what you had in your training set, or concept drift, which is with the input-output mapping, your X and Y changes in the world compared to your training set. But to ground this, if you're training a face recognition system now in, I don't know, when it's not too cold here in California, you get faces of a certain distribution. But as we approach winter, if it starts to rain more, people are wearing scarves, rain jackets, people look different, right? Or maybe we approach next summer, more people are wearing sunglasses, then the data distribution changes. Or if you train a system based on data here in California, but we then decide to deploy it, in a different country where people's dress differently or where their appearance is different, the world keeps on giving us different data. And so one of the jobs of, I think, us as machine learning engineers is to put in place systems that monitor this type of concept drift or data drift and fix problems as they arise. When you're out building machine learning systems, I have seen a segment of AI engineers that think their job is to do well in a test set, right? And so I've been in a bunch of these conversations where the machine learning person will say, look, I did well in the test set. My job is done. But then a product owner or business owner will say, no, your system doesn't work. Look at all the ways it does not work. And then if the machine learning person says, well, that's not my problem, I do well in the test set, I think that's not a constructive way to move it forward. So I encourage you to think of yourselves, if you're building a machine learning system, I think of my job as building something that works, and that can be different than building something that works on the test set. So if ever you're working on a product and someone says, I know you did well on the test set, but your system doesn't work, I would encourage you not to respond, but my job is to do well on the test set. I would encourage you to think about why doing well on the test set doesn't translate to doing well on the application that people actually care about, and then they'll lean in and go and fix that. Right? And one of the common problems for why doing well on the test set doesn't translate to doing well in real life is if the data distribution changes, in which case you may need to update the distribution of data you're training on in order to capture whatever has changed in the world. And just a few other examples. I feel like, the world gives us new data all the time. So if you're building a web search engine, sometimes a new politician is elected, or there's a new movement, or some new video goes viral, or I don't know, Taylor Swift releases a new album, I don't know, whatever. And then people are suddenly searching for a brand. I thought I'd get a laugh from that. No, all right, no Swifties here. All right. But then suddenly a lot of people are searching for a brand new thing. And so the distribution of data you get is different because the world has changed. I've done a lot of work in factories. There's actually a reasonable chance a cell phone you have in your pocket may have been inspected by software that, my teams wrote. But sometimes the materials change, or there's a new machine installed in the manufacturing line, and this machine makes a new type of scratch on the cell phone. So data changes in inspection lines as well. Or one thing that actually surprised me, when working on self-driving cars, one of the teams I was working with, we trained a lot on data in California. And then when we took the cars to Texas, you and I as people, we can drive just fine in, California or in Texas. But it turns out the traffic lights look really different in Texas and California, right? So it's traffic lights, horizontal, vertical. I think part of it is, there are very high winds in some parts of Texas. So a lot of traffic lights tend to be strung up differently to be robust to high winds, right? And so traffic lights actually look pretty different in Texas. So the models we train in California, they don't work in Texas because we get new data, refresh the data. So a lot of that is a process of monitoring and maintaining the model, even when something in the world changes. And before going on to monitoring the model performance and maintaining it, one interesting difference in performance between this and this is Option one is a very simple model, right? It basically has one parameter, which is epsilon, the fraction of pixels that change. And so this, because it's so simple, is actually very robust to changes in distribution. For example, say it's a hot summer and a lot of people are wearing sunglasses. Well, the fraction of pixels that change, right, even when people are wearing sunglasses, doesn't change that much. Maybe if it's Halloween and people are wearing crazy large costumes, maybe that would change. But this is actually a very robust algorithm because it's so simple. In contrast, if you trained on data with no one wearing sunglasses, because, it's not, sun's not that hot these days, right? Then with everyone starts to wear sunglasses, this is actually less robust. So one of the advantages of very simple non-machine learning based systems is they may be less susceptible to data drift, because maybe I tuned this parameter epsilon, to a limited data set, but even when the data changes, this tuning is quite robust. But if I train a neural network with, say, thousands or tens of thousands of parameters, then I'm more likely to have overfit to people without sunglasses. So if people start wearing sunglasses, you're more likely to have to update this model, right? And if you are building a sorry. Right, cool. Boy. If you're building a system, it turns out to be incredibly helpful if you can get user permission to stream a little bit of data back to your cloud-hosted service, so that respecting user privacy, being careful of opt-in, transparent privacy practices. I think that privacy is really important, right? So do be transparent, do the right thing for users. And if you're able to do that and get a little bit of data back to your cloud to plot dashboards, and maybe one practice that I've seen is when building a high-stakes application, one good practice would be to gather your team together and get a diverse set of opinions on all the things that could change and all the things that could go wrong. And I've built quite a few machine learning systems, and I found that when we sit down and brainstorm all the things that could go wrong, including the data distribution changes, I don't think I have ever seen something go wrong in real life that we did not identify as a possible problem. I might be wrong, but at least right now, when we sat down, we really brainstormed all things that go wrong. I think I have yet to see something go wrong that was not on the list of stuff that we brainstormed, right? And so if you brainstorm, and this is true for safety critical applications as well, right? It turns out creative teams, you can actually think of all sorts of things that could change the data or things that could go wrong. And that then lets you try to design a set of dashboards or metrics to put in place to monitor whether or not any of these things that you think might go wrong actually do go wrong. So we may put in place dashboards like how often, it turns out re-authentication is a common thing. How often does a user need to authenticate twice before they're let through? That's actually a sign of user frustration, right? So let's build a dashboard to do that. How often does a user have to try twice? Because it probably means something went wrong the first time. How often do you accept versus reject the user? And what is the latency of the system? And I find that just as it's difficult to know in advance what's in your data, it's actually difficult to know in advance what dashboard would be the most useful. And so the best practice I tend to recommend is brainstorm a lot of things that go wrong, brainstorm a lot of metrics, and then just, create very rich dashboards where this is time, latency, time, re-authentication, right? Time, the number of zeros versus ones, and then draw plots over time to see how these rates trend over time. And if you're able to have a lot of dashboards and sample and just, look at some of the data for where you suspect you may be making a mistake, that often is then a good way for you to have a higher chance of spotting when there might be a problem. And in the times that built large dashboards with 20, 30 metrics, I found that it's surprisingly difficult to know in advance which dashboards would turn out to be useful. I think in exploratory data analysis, in data science, again, because we often don't know what's in the data or what the data will give us in the future, we just, frankly, plot a lot of stuff and then go and figure out from there what is interesting, right? So the cost of plotting something in the Jupyter notebook is fairly low. So let's just plot a lot of stuff, have a lot of dashboards. And if you end up with 30, 50, 100 dashboards tracking these metrics over time, then hopefully in a few days or a few weeks, you figure out that a lot of them are really boring. So we figure out that, latency is just not a thing because with cloud-hosted deployment, it's just very constant. So, let's get rid of that because that's just a very boring plot. I'm just not worried about that. And so we often plot a lot of things and then prune back to then have a smaller number of metrics that we track and monitor for the long term. And then eventually, when you get a sense of, this being the normal range for some metric, you can then also put in place upper and lower alarms, so that if it ever goes above or below certain bounds, they'll trigger an alarm, like page someone to take a look to figure out if something's gone wrong. That makes sense? And so unfortunately, just because you train a model a lot of the time in a real world production setting, it doesn't mean you're done, because you deploy it and then the world will give you surprising data, and having a plan to monitor what happens as well as to maintain the model, meaning get new data, update the system, to fix problems as they arise. That is often an important part of, the practicalities of, deploying a machine learning system as well.